Okay, I'm Alina, and my talk is about speed, so I speak very fast.
Thank you. And one more thing, we need to click on this. No, okay.
Okay, so this talk is based on the work I've done with Shangyang, Daniel, and Paolo on the track Inference pipeline. And so you've seen in Ryan's talk the exatrack pipeline, and basically we started with like a baseline implementation of all the steps, and we tried to speed up the different steps. Now, because as I mentioned on Tuesday, the most expensive steps were like build edges and filtering. These were like they took so much more time than GNN, so we focused on BEM first. Okay. Okay, so first we speed up build edges using a radius graph type approach, and then
You have to turn the mouse around. You're holding.
okay. Okay, I think I'll just go all the way.
That's not working.
No, but if I click this, it was not showing the.
Oh, okay.
Okay, so we addressed build edges. We replaced the labeling from TV scan with like a foo graph that does weakly connected components. And then for the embedding and filtering, which are like MLP networks, we use automatic mix precision, which really speeded up things. And finally, so we went from 14 seconds to less than a second.
Sorry, can I stop that? I'm probably too stupid. How do I read this graph?
Okay.
Is foo graph doing all of this?
No. It's like
every column is an improvement.
Yeah, but it's an improvement on what part?
Okay, so the second column improves build edges with phase.
Yeah, but so I read phase is only used for the edge building or what for the graph building?
Yeah, it's just this one.
Okay.
And then this one, foo graph just does label. And
I could not associate in what color, what column made effect to what line. Yeah.
I went to, and then mix precision just does spreading and filter. And then finally this one build edges. Okay, so and this speeds up the computing performance scales linearly with the number of input spaces.
You're missing the arrow on the right-hand side of the figure.
Thank you. Okay, but we need a mechanism to integrate the pipeline with C++. So we were converting, we tried to convert the pipeline to, especially the deep learning parts to Onyx in order to overcome the multi-threading and be able to run that and integrate the pipeline with ACTS. So the initial pipeline was in Python. We tried to, we worked to move it to C++, FRNN. Daniel did a lot of work on implementing FRNN in CUDA with libtorch. For track labeling, we use QGraph. And when we converted embedding, filtering, and GNN to Onyx to use Onyx runtime. However, embedding and filtering, they work great, but the GNN does not really work because of this operator, the scatter add, which does the aggregation in message pattern. And then we decided to switch to TorchScript instead. Now, no matter what you use, Onyx or TorchScript, you can use this open source software from NVIDIA, TensorRT, that does optimization behind the scenes. And also they have this tool called Torch TensorRT that can convert Python models to TensorRT and kind of like convert only the possible parts, and then you can actually fall back on PyTorch to run the parts that cannot be converted. So in terms of the GNN, the big problem is with scatter which is not implemented, and you cannot convert it to Onyx. Or I'll come back to this a little bit later. So we can look at other domains to see how people are implementing real-time GNN inference. And one domain is autonomous cars, or like 3D object detection on these LiDAR images. Most of the approaches use just MLPs and convolutional neural networks, but there are also graph neural network approaches on this problem. So basically, object detection, you have images of on the street and you try to identify cars, people, and bicycles or pedestrians. And most of the approaches use kind of like a two-step approach, where the first part is an MLP and the second part is a CNN, and they are connected with a scatter operator. However, the GNN actually takes between 8 and 36 times longer than the state-of-the-art approaches, even if in most cases the accuracy is the best. So they have like an MLP part and the 2D CNN. They are connected to through the scatter add. Now, of course, in order to speed up this architecture, people use C++, Onyx, and TorchScript. However, in this particular paper, researcher presented a case study on optimizing the state-of-the-art point pillars, 3D object detection. They evaluated the conversion to Onyx and TorchScript, and they found out that TorchScript works better on MLPs, and Onyx works better on the convolutional neural networks because of the sparseness. And plus, the scatter operation in this particular study is implemented in C++ with the CUDA library. However, what other people do, they use what's called the tool from NVIDIA called NVIDIA called Graph Surgeon, that kind of like cuts out the scatter add from the network and replace it with the CUDA implementation. Now, when you have a large GNN network, you have many scatter adds, so that will be a pain to just like go and cut that out and replace it with whatever you want. So in the latest version of Onyx, this reduction part of the scatter add is implemented. However, it doesn't work in Onyx runtime, and you cannot yet. And also in PyTorch, it's not implemented, so you cannot convert from PyTorch to Onyx and get the correct results on this. There are some other tools available. With Olive from Onyx is a Python package that automates the process of accelerating models with the Onyx runtime. And then Glow from PyTorch is a compiler that optimizes the models for different hardware accelerators. And following Javier's talk, I looked at some new developments. However, on GNN. So one of them is about speeding up the inference with pruning. This approach uses lasso regression to identify feature dimensions that have higher influence on the output, and things that and hidden features that you can reuse in order to reduce the supporting needs. However, the speed up is not that great. It's just like 2.27. And then very recently, a group from Georgia Tech proposed this GNN framework, which is like a general framework for optimizing message passing and converting it to running it on FPGA. So most of the other work is focused on graph convolutional networks, but this framework can deal with any type of architecture. So most of the research on inference optimization on speeding up things is focused on training and not on inference. Most accelerators are focused on convolutional networks because they are sparse and that they can be easily optimized. But there are some new approaches that we can try to speed up inference.
So this graph surgeon thing literally changes the generated code, the target code.
You just go and cut the part that you don't like.
From the CUDA which is generated. Okay. But by hand.
From the model, yes.
Oh, from the model, not from the
Yeah,
generated. the
so
target code.
programmatically you write a program and you can just like use the surgeon API to grab that and replace it with whatever you want.
So how difficult, if you come back and show this other graph libraries, how difficult was your experience to port from one graph description to another if you now have like a new, let's say there's a new library out that promised to be super clever. How difficult is it usually to port from one to another, because you don't want to start from the beginning, no?
So from one model to another.
Not a model, like really at the end this is a description, right? And now imagine you have a second library that is just supposed to do the same, but claims to be n times faster.
By
or
library, you mean one of these accelerators?
yes, exactly.
So like you have the PyTorch model and you go from Onyx to something.
That's
what
my
you said.
question. Or so we find one for FPGAs that suddenly says like, here's an FPGA library that should do what Onyx is doing. Do we have some experience how portable our pre-trained models are?
Like, what do you mean? Between hardware or?
No, on the at the end it will probably run on a different hardware. But what we probably don't want to do is retrain, redo all the job. But the only thing you want to do is, supposing you have a library that says we can do the exact same graph,
just changing,
but change the library that does actually the computation.
So, I mean, I have not like done it myself. So, but like I've seen it in this 3D object detection done in like by multiple repositories. And,
But
I can
but
probably
you went from Onyx to Torch script, so you have done it
No.
once, right? Or somebody else.
no, so we are not going from PyTorch to Onyx to Torch script.
Mhm.
We are just like doing PyTorch to Torch script. And eventually, if this Onyx will work, we can just like.
I should have asked it way easier the question. Is there a need or an existence of some meta language that describes basically that's our model? Is Onyx what everyone uses? I don't know. Is that
There was a paper in ACAD that converted to C++ code. They convert models to C++ code.